Okay, I think we'll go ahead and get started. I'm Devin Brown. I'm on staff here at IEN, and I'll be introducing our speaker today. I'm substituting for David Gottfried, who is traveling to Seattle for the NNCI annual meeting that's being held at University of Washington. Our next Nano Tech will be 2 weeks from today. And that talk will be Surendra Chavan from Vicapsis, and that talk will be on current and future cell therapies for treatment of type 1 diabetes. So that's the next Nano Tech that's coming up. But today I have the pleasure of introducing Dr. Michael Varenberg, who is an assistant professor here in mechanical engineering at Georgia Tech. Prior to Georgia Tech, he was assistant professor at Technion, Israel Institute of Technology. And also he has held a position as a researcher in evolutionary biomaterials at Max Planck Institute for metals research. So today he has a really interesting talk, and the title is Bionics and Tribology, Adhesive and Frictional Dress of Elastomeric Surfaces. So please welcome Dr. Varenberg.
Okay, hi to everyone. So, millions of years of evolution have led to appearance of numerous biological systems that can serve as a source of inspiration for various technical solutions related to tribology, which is the science and technology of interacting surfaces. So, it is possible to look at the surfaces that are found in different attachment structures in animals, and we can recognize there several structures that can be associated with two main groups. The group one is shown here, that is associated with smooth surfaces that bear several structures that also have lubrication on top of them. So you can see here moth, bee, bat, and tree frog. And even looking at your fingers, you can find something like this. So we also possess certain structures that help us to grasp things well. So one group is smooth surfaces. There is also another group that is based on hairy microstructures that are shown in this slide. And these surfaces possess tiny hairs that are terminated with thin film structures of different sizes. And examples that you see here are for beetle, fly, spider, and gecko. So we can learn a lot from these structures. The question is how. And in principle, thinking about questions that need to be answered when working with these surfaces, first of all, we should think about what are the mechanisms that are hidden behind the effective performance of these structures, and whether it is possible to abstract these structures and to build something similar based on simple engineering materials and use it for technical applications. In order to answer these questions, we need to know first how to model biological surfaces using engineering materials, and also how to test them adequately in order to measure forces that are generated in between surfaces. So first of all, I would like to talk about these more simple questions, and then I will give you several examples of what we did in this direction in finding how to mimic the surfaces and what they can be used for. So in order to model biological surfaces, we use elastomers, which are able to recover from large deformations and are also able to dissipate mechanical energy. So there is a sort of good correspondence between biological, very complex structures and simple textures that can be made from artificial materials. Two materials that we usually use are PDMS, polydimethylsiloxane, which is a two-part rubber-like material that cross-links within several hours at the temperature that is a little bit higher than room temperature. And polyvinyl siloxane, which is also two-part rubber-like material that is used by dentists as a wax, dental wax, to copy what we have in our mouths in order to make prosthetic fixtures. And this material polymerizes within a really short time, 5 minutes at the room temperature. Now, technique that we use to build these structures are based on soft photolithography, which is creating a photoresist layer on top of silicon wafer, and then pouring PDMS, for instance, that cross-links in contact with this template. And then it can be peeled and used for different experiments. And we also use metal grids prepared on a thin sheet metal that has certain grids that are created by lasers that have through opening. And then again, we can use polymers that solidify relatively slow, relatively fast, and then before they get to the other side of this metal grid, they solidify. We can then peel them off and use in different experiments. Now, the apparatus that we built to test these structures is shown schematically here. So it consists of two main units. Unit number one is used for displacement. So it consists of 3 stages. And on these 3 stages, we fix mating counterface, which is usually made from glass material that has 1 rotary degree of freedom, which allows to adjust to self-align when it comes to contact with its counterface. The other sample that is patterned is cast from either of the 2 polymers that we work with, and it is fixed to a measuring lever that consists of 2 load cell, 2 force sensors that help us to measure normal and tangential forces. So when the mating surface is brought in contact with patterned sample, a normal force gauge is loaded, and we can control the normal load. When the sample is dragged in parallel to the contact plane, we can measure friction forces by analyzing deflection of this sensor. This device is built to be very small, and it can be fit into the vacuum chamber of scanning electron microscope, because it is good to measure forces that are generated by different structures, but we also need to see what these forces do to the tiny structures that we build. And this is one of the recent examples of the surface texture that is loaded in normal direction. When this apparatus is assembled outside the ACM, we can place it under the optic microscope in order to see through the transparent substrate what is the real contact area and how it evolves in response to different forces that we apply to surface structures, which is extremely important in trying to understand how it operates. Now, this is an image, a photo of the device. This yellow rectangles represent force sensors that help us to measure forces generated here at the interface between 2 samples that are not really well seen. And these are the stages that help to move one of the samples in all 3 directions. The device is assembled on the cover of the SEM, and this is the vacuum chamber into which it can be pushed and to be operated inside. So first part of my talk will consist of discussing how we can mimic hairy structures based on thin film terminals on the ends of these hairs and what we can learn from them. So looking at these tiny hairs that are found in different animals that are evolved independently, we can see astonishingly similar geometry when we compare them together. So these are thin films found on the attachment hairs in beetle, fly, spider, and gecko. And you can see that they all look very similar. They all operate like thin film peeled to any surface, and you can think about duct tape that you attach to a table, for instance, and if you pull it in different directions, it will respond differently. So this is the idea that is employed in these structures. It is possible to explain it based on candle peeling model that is shown schematically here. So if this is the duct tape that I just mentioned, the force that you need to apply in order to peel it from the surface will depend on 3 parameters. One, on the angle. If you try to pull it in the direction of the film, it will hold well. If you will peel it in opposite direction, it will detach very easily. So angle is important. The second parameter is, of course, chemistry of the interface. And it also depends on the width of this film. So the contact area is not really important. What is important is the width of this film that determines the force. And this actually allows to use the available surface area in a much more efficient way. If we split the large contact into large numbers of small thin films, and then the force that we need to apply in order to detach the whole structure from the surface will be proportional to the total width, to the total length of all width summed together. So this is the idea, and we wanted to test it in, or at least to verify that the idea is correct based on measurements of real animals. And these are results that represent total peeling line length, the sum of width of all contact elements in about 20 different animals represented as a function of their body mass. You can see here that body mass ranges within more than 4 orders of magnitude, from several micrograms for mites to over 100 grams for gecko, and total peeling line ranges within 8 orders of magnitude, from several micrometers for mites to over 1 kilometer for gecko. And clearly you can see that there exists a good correlation between these two parameters. So we wanted to employ this idea, and we had to find the way how to create the structures with this thin film-based texture that will enable us to test whether it will work in artificial surfaces. So a technical solution had to overcome several problems, which are increasing the peeling line length without working with a large number of these projections, which is not very easy to make them. So we solve it by suggesting working with long wall-shaped structures. Ease of template fabrication and cast release. We achieved this by working with projections that are roughly perpendicular to the surface. And we also had to secure gradients in projection width, which is the property that is associated with real hairs that are found in different animals. So the solution, schematic representation of the solution can be seen here. So wall-shaped projections that narrows towards its distal end and has flexible flaps that can deform easily when they come in contact with the counterface. So we found a British company, a laser company, that was able to create tiny openings within larger patterns. These are 2 examples: hole inside the hole and through slot within the blind range. And this is an example of one of the first trials of the projection of the surface structure that we created based on this principle. Now, these are examples of wall-shaped microstructures that were created recently. So this is what we have now. An example of image of tungsten template that is laser machined to have structures that are used as a template in curing the polymer. This is an image of the projections that were created from polyvinyl siloxane cast against this template, and these are ACM images of the wall-shaped projections having different heights. And this is a short video that filmed in the ACM that represents how the structures operate when they are loaded in normal and then in lateral direction in two opposite sides. So you can see how these structures can invert themselves and attach themselves properly to the counterface. So in order to test their operation, we first focused on verifying the idea that pulling angle is indeed important parameter. So we designed the test in which the surfaces were loaded normally this way until a certain very light load was achieved. And then we applied tangential displacement to align all these structures in the same direction. This is the result of force measurement. Friction force represented as a tangential displacement. Black line represents friction force, and a gray line shows normal force. So when tangential displacement is applied, the surfaces initially deform elastically, and then they start to slide. This is the point of sliding inception. This is the point where surfaces overturn and align together. Now, actually, we wanted to test pull of force when the surfaces started to be withdrawn from each other at different points. And this is a schematic representation. So after certain pre-displacement is applied, we start pulling our counterface at different angles and measure the forces that are generated at this moment. So black line represents tangential forces generated at the time of the pulling, and gray line represents the normal component. So the lowest point actually gives us the pull of force. The force needed to be generated in order to detach surfaces from each other. And this is the summary of all the tests that we made to study pulling angle, the effect of pulling angle in preliminary displacement. So color here represents normal force, and it can be clearly seen that there is optimum for the pulling angle and for the preliminary displacement, which it suggests or proves that indeed the surfaces can be used in adjustable way. So the pull of force can be efficiently changed when pulling the surface at different directions. When angles are large, it detaches with zero force. When angles range within 70 to 100 degrees, then the force generated achieves maximum values. And we also found that the best results are achieved when preliminary displacement is equal to half the distance needed to start sliding, so somewhere here, which can be explained in the following way. When the preliminary displacement is not large enough, then all these projections are not aligned well, and they do not perform efficiently. When preliminary displacement is very high, then sliding starts, which means that each of the structure starts sliding, sticking, and sliding, and they all stressed to a different extent, which again results in not uniform, not efficient performance. However, somewhere in between, there is an optimum range when the forces are maximum. Another topic that we studied with these structures was the effect of contact splitting. It is accepted to think that splitting large contact into smaller structures allows to withstand detrimental effects associated with increasing in roughness. So we wanted to test the correlation between contact splitting and roughness of the substrates. So we prepared, actually we used the same wall-shaped microstructures and cut them with the blades to split long walls into much shorter sections. And we tested them against 12 or so different substrates having various roughnesses. What you see here is the same images of one wall-shaped projections in contact with different rough substrates. And this is the result. So we can indeed see that when we have a smooth surface, then pull of force is not affected by contact splitting. So long walls operate the same way as the walls cut in shorter sections. But when the roughness starts increasing, we can clearly see that pull of force drops quite fast. And when we have structures that are split into shorter sections, then this split surface is able to withstand detrimental effects associated with roughness in a much more efficient way. And what you see here is the result of measurement of friction against several rough substrates. First of all, we can see that increase in roughness results in decrease in friction forces, which is expected. And we can also see that frictional forces measured with wall-shaped microstructures are extremely high, with a ratio of friction to normal load of over 100. You can see it here for low loads of 2 or 3 millinewtons. We get friction force of about 500 millinewtons, which is very efficient and large friction forces that may find applications in different fields. And this is just one example of possible application. Pick and drop processes that are associated with, for instance, handling wafers in semiconductor industry. Usually, it is made based on suction vacuum systems that require pumps, sealing, and quite bulky installation of quite bulky systems. So, using gecko-like microstructures can make it probably much more efficient. But this is a question of future. So far, we didn't have any collaboration in this respect. The second example that I would like to present here is related to working with smooth structures, especially with hexagonal surface textures found in tree frogs. Looking at these three animals, you can clearly recognize that they belong to totally different group. There is not much common in between. However, if we look at their contact surfaces, we find great similarity between them. All of these three animals possess hexagonally shaped projections that evolved in response to interaction between animal toes and the substrate. So the question that we had to ask ourselves first was what was the reason that led to appearance of similar structures in different animals. And thinking about the conditions in which these structures operate, we can see two different things. One, these animals can stick to vertical and, in certain examples, overhanged surfaces. And the second, all three of them can jump. So high friction forces are resulted. Given that all these textures possess some lubrication layer, it is important that clearly lubrication is known to reduce friction. So we had to find out whether these structures evolved in order to fight friction-oriented problems or to improve attachment. So the first hypothesis was that this texture is adhesion-oriented, and the explanation for this is shown here. There is a contact splitting principle that was defined around 10 years ago. So that says that if we split large contact into smaller subcontacts, if the contact area remains the same but number of contact increases, it should lead to higher adhesion force. And the second hypothesis was that the texture is friction-oriented, which is associated to the presence of lubrication layer. If you think what can happen with surface grip when surfaces that come in contact are separated by a lubricant layer, you can look at this car that, due to hydroplaning, loses traction with the road. So probably these channels that are found in between hexagonal projections are needed in order to drain the contact and to remove liquids out of the surface. So in order to test both hypotheses, we had to create these structures. And this is a schematic representation of hexagonally shaped projections that we cast from different materials. We worked with polyvinyl floxane and PDMS. This is schematic with 3 parameters that are important: height, period, and size. And this is the same image that shows PDMS structures, and we casted them to have different aspect ratios, area densities, height, and size, period. So we ranged all parameters in order to see how they operate. So first of all, we tested the attachment ability in order to verify this contact splitting principle, and it appears that the idea is wrong. So what you see here are pool of forces represented as a function of number of contacts. So when we have more hexagons on the surface, while the contact area was the same in both cases. This is lubricated contact, this is dry contact. You can clearly see that despite the number of the surface projections increases by about 2 orders of magnitude, we have the same pool of forces in both dry and lubricated contact, which means that the contact splitting principle doesn't work here. So we turned our attention to friction hypothesis, and we tested the structures in both lubricated and dry conditions. So this is the result of friction forces measured in non-textured and textured surfaces in lubricated conditions. So which is more or less identical or similar to real world application. So we can clearly see that the surface that was not textured, and we always use some reference surfaces that did not have these projections. So not textured surfaces has shown very low friction force, while textured surfaces clearly demonstrated that as the structured surface slides against the surface, against the substrate, friction force starts to increase. And we can see the same in images of the tree frog that jumped on a tree trunk. If we zoom at the region of the interface between its toe and the tree, we can see the trace of initial sliding, which means initially there is a lot of lubricant at the interface, and during sliding it is squeezed out until the animal is able to get a good grasp and sit on the surface. we were really surprised to see very interesting results in testing dry sliding condition. So what you see here is performance of smooth surface sliding against the substrate, and we can clearly observe, recognize here stick slip motion, which can be explained in the following way. When we have a rigid surface that slides against the elastomer, which cannot really slide in an accepted way, the surface behind the contact is in tension, the surface in front of the contact is in compression, so it buckles, and then a small wave is created in front of contact that runs in between two surfaces. This leads to stress relaxation, and surface actually moves not as a result of sliding, but as a result of worm-like displacement at the interface. So this is how smooth surface operates. And surprisingly, textured surface, hexagonally, these samples with hexagons appeared as sliding in a smooth way. In order to explain this behavior, we developed this toy model that in a very simple way allows to explain that the reason is statistical variance in properties of the surfaces that come in contact. So what you see here is a body that is placed on the moving conveyor, and this massless block is connected with a spring to the wall. Then the three parameters that we changed here are spring stiffness and kinetic and static friction at the interfaces. So when conveyor starts moving, then the block actually sits on the surface due to static friction and moves together with the block, and the spring is loaded. When the elastic stress, when the elastic force achieves a certain value, it becomes larger than the static friction, and the block moves back until kinetic friction is achieved, and then the process is repeated again. So these were initial conditions, and we started to split this block into large amount of small structures, while the total stiffness and forces in some remain the same. So the interesting thing, when we split large surface into two smaller surfaces, if the properties, the friction and the stiffness in both bodies, if the properties have the same values, then actually the friction force behaves in absolutely the same way. However, if we introduce some statistical variance in all three properties, then differences start to be seen. Friction force, shown as a function of displacement, appears to have some fluctuations that resemble more natural behavior of the surfaces that come in contact. And so this is what was obtained for just two elements. If we increase the number of elements, then these are the results obtained for 50 small blocks or 5,000. Clearly, the sliding becomes much more smooth, and we do not see this sawtooth-like behavior characteristic of moving of sticky elastomers. And the interesting thing that if we increase variance, then actually friction force appears to be similar to the result that we seen on the previous slide. So very simple model. Toy model allows to explain the differences in between surfaces that possess different number of elements, if these elements have some variance in their properties. So we were also interested to study the effects of different geometry parameters, and the two parameters that we worked with were area density and aspect ratio. This figure represents friction force as a function of lateral displacement, and you can see in red behavior of a smooth surface that also shows very pronounced stick-slip behavior. And blue lines represent behavior of structured surfaces, and clearly we can see that it is possible to change the frictional forces within a wide range. So we wanted to learn what is the main parameter that determines this adjustment. So what you see here is friction force represented as a function of area density, the area covered by these hexagons over the total apparent area. And we can see that actually area density does not affect friction force. And this is two images from ACM that suggest some explanation. So when we have different area density of the projections having the same aspect ratio, clearly the normal load is the same in both cases, which leads to higher deformation when we have less elements in contact, and they are tilted as a result of shear load, and then actually contact area in contact areas in both of the cases is more or less the same due to the same normal load that is applied in when testing this property. And when contact area does not change, obviously this results to in the same friction force. When looking at the effect of aspect ratio, here we start seeing some results, and clearly some optimum can be observed. Again, it can be explained based on geometry of different, on the images of different surface projections shown here. When they are low or when they are high, they are characterized by different stiffness, and when shear stress is applied, they bend to a different extent. The surfaces that are very low keep their base area in contact, while the projections that are very high, they bend and fall on sides. So in both of these cases, contact area can be quite large, so measured friction will be high. And somewhere in the middle, there exist several geometries when the stiffness of these projections is not large and not low, and they not fall aside, they are not able to maintain the initial shape, they just stand on a corner, which results in lowest possible friction, and we can see it here. So it was found that aspect ratio is the main parameter that determines the system response. And as in case with wall-shaped projections, we also started thinking about possible applications, and the one that is really appealing was found in safety resource. So if you think about this device, you can recognize that it consists of 3 different elements. We have here blades that cut the hair. We have here a rubber strip that is used to stretch the skin. If you remember when we shaved ourselves before these products come to market, with one hand we stretch the skin, with the other hand we remove the hair. So they introduced this element that requires to have high friction, and there is also a relieving unit that makes us feeling pleasant when shaving our hairs. The interesting thing that this element actually stands in the condition of hydroplaning, because we apply shaving foam in order to make the shaving process easier, but this shaving foam creates a lubrication layer here, so the stretching, the skin stretching is not really efficient. So we thought that this region is a good place where we can test our hexagonally textured surfaces, and we proceed in this direction. Now, how we were sure that friction is important here? If you look at the evolution of safety resource, you can clearly see that the number of wipers that are found in this stretching unit is proportional to the number of blades. When Gillette just came to the market with their Sensor XL, they had only 2 blades and they have 5 wipers. The next one had 3 blades and 9 wipers, and what we have now operates based on 5 blades and 15 wipers, meaning that roughly saying each blade requires 3 wipers to have sufficient to have skin stretched sufficient. So we wanted to test how our hexagons operate in this unit. So we modified real safety razors. We removed blades and relieving units and left only skin stretching elements. This is a schematic representation of the device that we use to test the idea. This is not a wrist cutting machine. This is just a device that helps to hold safety razor, real safety razor, as the one shown here, with all elements that we didn't want to test removed. We tested friction of skin stretcher against the human skin at the inner surface of the forearm in the presence of the shaving foam. So what we applied the load that it was more or less similar to the one that is applied when we shave, and the friction force was measured with a force sensor that moved with respect to the hand. And these are the results that we obtained. First of all, this is a comparison of biomimetic structure and real wipes found in safety razors that are commercially available. And this is a characteristic example of friction force measured as a function of displacement. C stands for commercial, B stands for biomimetic. So commercial structure was able to generate certain force when this is the curve, and this point represents the onset of steady sliding. While testing biomimetic surface in the same conditions, this is the result that we have obtained. It was able to generate about 2 times friction of what we use in real life safety razors. And this is the summary of all the results, where friction coefficient is represented as a function of surface texture. So we have here skin stretching elements by Schick, by Gillette, made from original materials, but we had to cast similar structures from the same material because the idea was to test the effect of geometry and not the effect of the material. So we created our the same geometry based on our material by just molding, by creating templates against the original surfaces and then casting these structures made from our materials. And what we can learn from here is that, for instance, Schick shows the same friction as smooth surface, so there is no improvement due to surface structure that they sell. Gillette performed a little bit better, but it showed the similar results as the worst biomimetic surface texture that we had, while the best biomimetic structures performed really significantly better than commercial skin stretchers that are used nowadays everywhere. So after this work was published, Gillette came to us with the question whether we can collaborate on this topic. So we sent to them our structures. They tested them, and eventually they told us that they're not interested, which was sort of strange to me. And when I started thinking about this topic, I came to the conclusion that the problem was associated with that these devices, safety razors, are designed to have designed to become obsolete because they want to sell them again and again, so they do not want them to work too well. And this is the explanation. So what you see here is an image of the pack of safety razors. It says that, roughly saying, one cartridge lasts for 1 month, which is not really logical because they are made from, the blades are made from high-speed steel, and they are coated with diamond-like coating, so they should be extremely wear-resistant. And it is very strange that just within 1 month of using against human hair, they wear so that they cannot be used. And probably this is the experience of most of you. These devices do not hold more than just 1 month. Now, and what is the reason? Now, this is the schematic. These are the blades that actually do the work, and this is a schematic representation of the skin stretching element that needs to have high friction. Now, so we have high friction here, which is required, and we have low friction here because this second, as they call it, guide, is covered by lubrication layers, sort of gel that generates low friction, and then the device operates well. However, what happens after about a month, when this layer is removed? Then we have high friction here, skin is not stretched in between these two guides, and the blades start cutting skin that creates wavy shape. And actually, this was a very interesting conclusion. So at that time, I had the safety razor that I was about to throw out because it didn't work well. So I took it to the lab under the microscope, and I was amazed to see that the blades were like new. So they could operate still well, but the device was not functional already. So what I did, I removed this second element that created high friction on the wrong side, and miraculously the device started to work properly. Since then, I do this little surgery each time I start a new safety razor. And it appears that they work about 6 times longer after this small operation. And another very interesting result is that I stopped cutting myself. Because beforehand, every other week, every other day, I cut myself, probably due to that this friction was still too high. Since I remove this element from real safety razors, I can do it much more safer. And small description of how this can be done. Really simple. What you need is just a safety pin that you have to stick from the back of the safety razor. And then this relieving unit comes out really easily. So this is a relieving unit for them, right? Because this is a golden goose that brings them golden eggs, because we pay 6 times more than we should. So after it is removed, this is what we have, and this safety razor operates extremely well. Recommended. And this is more or less also to summarize. We worked with wall-shaped microstructures that are able to demonstrate directional adhesion and are tolerant to surface roughness, and are able to generate friction which is really high. And hexagonal surface textures are found to prevent hydroplaning when in lubricated conditions. They're able to eliminate stick-slip disturbances that are very detrimental because they cause noise, energy losses, problems with accuracy and wear. in various engineering devices. And using hexagonal surface texture, we can also tune friction within quite a wide range. And I would like to thank all those who inspired me and helped to run all these tests. And of course, the institutions that participated in funding this long year research. And thank you for coming here. That's it.
Questions?
When do you use PDMS and when do you use PDS?
When do you
If we have surface structures that should be characterized by flat top, then we use PDMS and we cast them against soft photolithography prepared structures. When we work with wall-shaped projections that come in contact with vertical surfaces, and it is not important what we have at the bottom, then we use templates that have through openings, and then we use PVS, which enables us, which actually solidifies fast before the polymer gets to the other side. So it is a matter of speed. If we want to cast it fast, we use PVS. If speed is not important, when we use when speed is not important, we use PDMS. Yes. Young's modulus of these two materials is very similar, about 2 megapascals also.
So I was wondering with regard to very nice presentation, whether there is any applications or extension of this to systems like looking at adhesion forces or adhesion of biological systems like cells and tissue. Have you any thoughts on that?
Well, these structures are quite large to be operated together with cells. In principle, they can be used in contact with biological tissues. I know that hexagonal surface projections were involved in creating devices that move inside digestive tract, because for different types of visualization, there is a need for a device that can move inside our body. So yes, it can be used in contact with biological tissues.
Can we go back to the comparison slides of the hexagonal and the commercial products? So for the plots on the top left corner, what do you think would be the reason, like it takes much longer displacement for your structure to reach a steady force?
Here,
yeah.
This is associated with that you need to drain, you need to remove the shaving foam in this example from the interface, and it takes time.
So they have.
So actually here it is able to remove more lubricant, and obviously it takes more time. You can see that slopes here are more or less the same, so the rate of lubricant removal is more or less similar, but these structures have more capabilities to removing, to removing it more efficiently.
Thank you for the excellent talk. I have a question about the function of the sticky fluids or sweet secreted by a frog or a lizard.
Okay.
So what do you think the function of the liquid? Is it for lubricating or for?
Well, first of all, lizards have dry systems, so they don't have fluid. So hair-like structures found in geckos, they are dry. So liquids are present in frogs, And I think that its purpose is to generate attachment. So they attach themselves due to capillary effects. So that's why they need liquid. But in order to grasp things and to jump, they need to have not that much liquid at the interface. So they need liquid, but they need to be able to adjust its amount. So that's why they need these channels that help to drain lubrication out of the contact and generate high friction. So texturing for high friction, liquid for high adhesion. Or maybe not high adhesion, but to some gain in adhesion.
Any other questions? Thanks for the tip on the razor. I can't wait to try that at home. So. Let's thank our speaker again.